You should take a look at section 6.6, which is on the symmetric group. And Richard Taylor, who's a professor in the department, will be subbing for me on Friday. And then the homework, he doesn't know the homework due Monday, but here is the homework due Monday in section 6.6. And then Peter Green will lecture Monday and pick up where Richard left off on the symmetric group. So I want to just review very briefly the CELO theorems and their proofs that we did last time, and then do some cool applications for you where you see how these theorems can be used. So remember the theorem: if G is finite of order n, which is p to the n times m, and m is prime to pre, so that p to the n is the largest power of a prime dividing the order of the group, then 1, there exists CELO p subgroups of order p to the n. So there are subgroups of the maximum power prime order. Any two such subgroups are conjugate. So they form a unique conjugacy class of subgroups of that order. And 3, the number L of such subgroups satisfies L divides M, and L is congruent to 1 mod P. So a typical number that can always satisfy this is L is equal to 1. It's always possible that the CELO subgroups are normal and there's only one. Possible that L is equal to 1, i.e. that the CELO subgroup is a normal subgroup of G. That's certainly possible. Doesn't always happen, but that's something that could, any two such would be conjugate. There namely would be only one of them. So that would be a unique CELO P. And then, but there could be more, but in any case, under 2, they're all conjugate. So that's the content of the CELO theorem. Yes? No question, just a stretch.
I was wondering, what is the connection between normalness here?
You see, if there's, it's possible, one number L that divides M and is congruent to 1 mod P is 1, L equal 1. You can always try L equal 1. There may be other numbers that satisfy this, but there's always a possibility that L equal 1. If there's only one CELO subgroup, then by number 2, it says that it must be normal, because any conjugate of H would be a CELO subgroup. I mean, if you had a subgroup of order p to the n, so if H has order p to the n, so does H prime, which is GH G inverse, a conjugate of H. If there's only one CELO subgroup, then these are all equal to H. Because whatever this is, it's a CELO P subgroup. It has the same order. And therefore, H is normal in G. Conversely, if H is normal in G, there is only one CELO P subgroup. The reason is that any two of them are conjugate. So if you had another one, you'd be able to conjugate H into H prime. But saying that H is normal in G means that all conjugates of H are equal to H. Got that idea now? Good thing to fix in your mind. All right, let's recall the proof very, very quickly. I'm going to walk you through it. It's all about groups acting on sets via groups acting on sets. And the key principle is if G, all right, so the first thing you do is you have G acts by translation on set, I don't know, J of subsets J and G where the size of J is p to the n. So you take G of a subset is the subset G times J. That's what I mean by translation. So it permutes around the subsets of size p to the n. Because if this has size p to the n, then all products with G have size p to the n. The number of such subsets is equal to n, choose p to the n, which we showed is prime to p. So some orbit O sub j has size prime to p. So the stabilizer of that orbit has order divisible by p to the n, because the size of the orbit is the order of G divided by the order of the stabilizer. But the stabilizer of any orbit has size less than or equal to p to the n. Less than or equal to p to the n. That I sort of fudged a little bit, and this is for the following obvious reason. If J is in the subset and G is in Gj, then Gj is in the subset. All right? I mean, that's what it means to be in the stabilizer of this subset. If you act by the left on G, you stay inside the subset. All right? This gives the order of G elements in J. Right? Therefore, this number has to be less than the number of things in J. So the number of things in Gj has to be less than the size of J. So then I have a subgroup which has order divisible by p to the n, which has order less than or equal to p to the n. That implies that Gj has order p to the n and is a CeLO P. And that was the proof of 1. What is this doing over here? This isn't even my real eraser. Where is the real eraser? Oh, here's the real eraser. I'm sorry. Once we have a CeLO P, then we start doing orbit questions. So the next part 2, we change our set that we're acting on. You now have let H be a CeLO P, and let G act by translation transitively on the coset space of H, which has order M prime to P. Again, we construct a set of order prime to P, but now since we've proved 1, so that we have a subgroup called 1H. Now that we have a subgroup of order P to the n, we can change our set that the group is acting on to be this by translation. It acts transitively on it because it always acts transitively on a coset space. So the stabilizer of the coset GH is the CeLO P subgroup GH G inverse. Because the stabilizer of the coset H, we know this from our general action on. And we have to show that any CeLO P is of this form. So it suffices to show, so let H prime be a CeLO P and restrict G action on G mod H to H prime. Well, I claim this is a set of order prime to P. This is a group of order a power of p, right? Therefore, it has to fix something. Because if it didn't fix something, the orbits would all have size divisible by p. The orbits have size p to the a for 0 less than or equal to a less than or equal to n, because the orbits for h prime are of the form the order of h prime divided by the stabilizer. And the stabilizer is a subgroup of h prime, so this is a power of p. If all of these were divisible by p, then the sum of the size of the orbits would also be divisible by p, which it isn't. Because this total space that they're acting on has order prime to p. So some orbit has size 1, not divisible by p. And since it has size 1, that means that h prime fixes the point, which means that h prime is contained in the stabilizer of the point. But these groups have the same order so that h prime is equal to that stabilizer. So that's the proof of 2. And the proof of 3 is another group action on another set prime to p. So let's go through 3 again, because that's in some sense the most clever. Each one uses the previous to construct a different group action. The first one, we just knew that the order of the group was this, and we constructed an action on subsets. Once we had CeLO P subgroups, we have this set to act on. Now that we know they're all conjugate, 3, since all CeLOs are conjugate, have the transitive action of G by conjugation, not by translation, on set H of all CeLOs. This is the set that we're trying to count, right? This set, the stabilizer of H for this action is the group G sub H that we called the normalizer of H. So therefore the set H, whatever it is identified with G modulo the normalizer of H. Is a coset space because it's a transitive action. Right? So whatever this is, the order of this divides M. Normalizer of H contains H, so the order of H of this quotient set divides M. Because the index of H is M, so whatever the index of the normalizer is, it's a divisor of M. Right? Got that? Normalizer of H is between this and G. This total number is M, so whatever this index is the divisor of M. This index times this index is the whole index. Okay, divides M. That's the first part of the theorem. The second part is we consider the action of H on this set. Now consider the action of H by conjugation on H. Now G permutes them transitively, but H doesn't. For example, H conjugates itself into itself. So this fixes H. And I claim this is the unique fifth point. So all other orbits have size divisible by p, because the orbit is H divided by the stabilizer subgroup, which is a p group. And if all the other orbits have size divisible by p and there's a unique fixed point, then the number of elements in this set is congruent to 1 mod p, because it's the sum of things divisible by p plus 1. So all I have to show you is that there's a unique fixed point for the action. Well, suppose there was another fixed point. That would say if h prime is fixed by conjugation by h, then both h and h prime are contained in the normalizer of h prime. Because to say that h fixes h prime under conjugation means that whatever this is, it's a subgroup of the normalizer of h prime, which is exactly what fixes h prime when you conjugate by g. Okay, the problem with that is that they're both CeLO P subgroups of the normalizer of h prime. Because whatever the order of this is, it's some p to the m times m prime, and these both have order p to the n. So they're both CeLOs. In a new group, namely in that group, which is a subgroup of G. But we proved in part 2 that for any finite group, any two CeLO subgroups are conjugate. Therefore, they have to be conjugate in the normalizer of h prime. But the normalizer of h prime contains h prime as a normal subgroup. And remember, when we had a normal subgroup, it was the unique CeLO P. Therefore, h has to be equal to h prime. And therefore, this fixed point that we thought was a distinct fixed point is actually equal to h. Both CeLOs. H prime is normal in normalizer of h prime. So is the unique CeLO. So h is equal to h prime. And that's the final proof that the number is congruent to 1 mod p. There's a unique fixed point in the action of G. If you take the action of G by conjugation on the CeLO P's, it acts transitively. If you restrict that to H, any CeLO P, it has a unique fixed point, its own CeLO P. Doesn't fix any of the others by conjugation. So this is great. This is just great mathematics. What can you say? I wish I had thought of it. And it's absolutely the central result in the classification of finite groups. As I said, there's a huge project. I should have brought in my book on the Atlas of Finite Groups. A huge project in the late 20th century to classify all finite simple groups. The start is always the CeLO theorem. Always the CeLO theorem, because it gives you immediately, for any finite group, a large host of subgroups where you know they're all conjugate, you know about how many of them there are, at least you have some estimate on it, and you can try to build the group out of those subgroups. So what I'm going to do for you today is I'm going to show you how this affects the classification of groups of small order. So you can get some idea of how CeLO theorem can be used in action to describe all the groups of order 6, or all the groups of order 15, or all the groups of order 21. So remember what we've got so far. We know the classification theorems. We've shown if the order of G is P, a prime, then G is cyclic and isomorphic to Z mod PZ. If the order of G is P squared, then G is abelian. And there are two possibilities. It could either be isomorphic to Z mod PZ squared if there were no element of order P squared, or it could be isomorphic to the cyclic group. This is all G not equal to E, satisfy G to the P is equal to E. And this is, there's some element which doesn't have order P. All right, now we're going to do PQ. Two primes, and we'll assume that P is less than Q. One of them has to be less than the other. All right, let's make some observations about this before we do actual P's and Q's. Yeah, why not? So that we can get started. The first is there exist subgroups HP, HQ, CeLO subgroups of order P and Q. So may not be. So those divisors give rise to subgroups by the CeeLo theorem because we write the order of the group as P times Q, and P is prime to Q. So I apply it twice. Yeah.
We're assuming Q times 1.
Q is prime. Yeah, they're both prime. I'm sorry. Otherwise, we wouldn't know there was a subgroup of order Q. So it's like 6 or 15 or 20. Okay? Second thing is that as a set, G is equal to the product of elements in HP and HQ. Oh, both of these are cyclic. Isomorphic to Z mod PZ, Z mod QZ. That's from our previous classification because they have prime order. So whatever those subgroups are, we know what they are. They're cyclic groups. Secondly, as a set, G is the product of elements HP and HQ. So it's something of the form, let's say this cyclic subgroup of order P is generated by tau, and this cyclic subgroup of order Q is generated by sigma. So this would be of the form tau to the A, sigma to the B, such that 0 is less than or equal to A is less than P, and 0 is less than or equal to B is less than Q. Because the elements of HQ are the powers of sigma between 0 and Q. The elements of HP are the powers of tau between 0 and P. And I claim that if you take all elements in HP and you multiply them by elements in HQ, you get the entire group. Okay? Why? Well, this is just saying that the elements in HP represent the distinct left cosets of HQ. Now, namely, that this is G is equal to the union of tau to the A HQ for the different taus in, or for these 0 less than or equal to A less than P. Well, it's enough to prove that these cosets are distinct, right? Because each coset has Q elements in it, and there are P possible cosets for the P different elements in HP. So as long as we can prove that these cosets are distinct, they have to give us the whole group. And they're distinct for distinct tau and tau prime in HP, because if we had an equality, tau HQ was equal to tau prime HQ, that would imply that tau times tau prime inverse was an element in HQ, right? Which would imply that this element tau, tau prime inverse was in the intersection of HP and HQ. And the intersection of HP and HQ is a subgroup of both of them, so has order dividing P, but also has order dividing Q. And the only number that divides both P and Q is 1. So the intersection of these two groups is the identity. So if we have the equality of these two cosets, this element has to be the identity. In other words, we have to have the equality of elements in HP. So we already know, just from the CeeLo theorems, that our group is made out of these two cyclic subgroups. And the only thing we really have to figure out is how to multiply two things here. Right? And in particular, we'd like this, when you try to multiply a tau to the A, sigma to the B, times a tau to the A prime, sigma to the B prime, is equal to what? You have to write it as a power of tau times a power of sigma if you want to write it in this form. And basically, you have to figure out how to commute these two elements across. Right? What happens when you multiply sigma by tau and you try to turn it into a tau by sigma? Okay, so that's the whole problem of determining the structure of groups of order PQ. How do these two generators cross each other when you try to multiply them? So I'm going to work that out for you. Okay? So the first observation I want to make, which is kind of bizarre, the first observation I want to make is that this HQ is always a normal subgroup of G. This is completely general. HP may not be normal, but HQ is always normal, the bigger prime. And the reason is this. The number of CeeLo Qs L divides P and is congruent to 1 mod Q. Well, any number other than 1, which is congruent to 1 mod Q, is at least Q plus 1. But P is less than Q, so it couldn't divide P. Right? So the only such possibility is L equal 1. The only possibility, because Q is bigger than P. So the fact that it's normal means the following, that if I take tau, sigma, tau inverse, that has to be a power of sigma. Because whatever this element is, it's in HQ. And the whole structure of the group is that, so this says that tau sigma is equal to the sigma to the A tau. And the whole structure of the group depends on what this A is. That's all it depends on. Because so once I know what A is, I can figure out how to commute these two across. So this mysterious number A determines the group, and we have to figure out what are the possibilities for A. Now we're going to do some specific P and Q, and you'll get the feeling for it. So I'm fudging a little here. I mean, as I say, you now have to see that once you know what this number is, you can multiply something like this, something like that, and turn it into a power of tau, a power of sigma. You have to believe me on that. You'll just do that, quietly yourself. It's not hard. Let's try groups of order 6. Then we'll do P times Q is 15. Okay, so here, HQ is of order 3. It looks like this. 1 sigma, sigma squared. HP is of order 2. 1 tau. Okay? We have to figure out what's the possibility for tau sigma, tau inverse. Well, it could be sigma. No problem there. That would just say that tau commuted with sigma. Then the group would be abelian. Because it's generated by tau and sigma. If they commute, everything commutes. Tau sigma equals sigma tau. G is abelian. And in fact, you'll find it's isomorphic to Z mod 6 generated by sigma tau. Namely, sigma has order 3, tau has order 2. Since they commute, you can prove that this has order 6. And if you have an element of order 6 in a group of order 6, it's cyclic. So if this element was sigma, we'd get an abelian group. What are the other possibilities? Well, it's got to be some power of sigma. It can't be 1. You can't conjugate a non-trivial element into the identity. So it's got to be, the only other possibility is, could it be sigma squared? And the answer is, yeah, that's the same as sigma inverse. Because this is a group of order 3. And we already know a group that has a cyclic subgroup of order 3, an element of order 2 that conjugates that element of order 3 into its inverse. What's that called? The symmetric group. More generally, it's the dihedral group. The dihedral group, remember, contains a cyclic subgroup of order n, an element of order 2 that conjugates the element into its inverse. So here it is. So this is just, so G is isomorphic to the dihedral group of order 6. Also, in this case, it's the symmetric group on 3 letters. So here we've just shown, by this argument using the CeeLo theorems, that gave us not only the subgroup of order 2 and 3, but proved that the subgroup of order 3 had to be normal. And so when you conjugated, you had to get some power of sigma. It just proves to us that there are only 2 groups of order 6. If you get the first power of sigma, you get an abelian group, which is cyclic of order 6. And if you get the second power of sigma, you get the dihedral group of order 6, or the symmetric group on 3 letters. Okay? Now, You might say, well, that's probably what happens in general. And you'd be wrong. But in fact, why don't we do the general case of 2q? So order of G. Because then you'll see that the exact same thing happens. Namely, in this case, HQ is 1 sigma, sigma squared, sigma to the q minus 1, which is the same as sigma inverse. H2 is just 1 tau, right? And again, we find that tau, sigma, tau inverse is some power of sigma. And I claim that this A is plus or minus 1. So there are only two possibilities. Well, it's really congruent to plus or minus 1 mod q. Because if you think of these powers, it only matters what the power is mod q. If q minus 1 is congruent to minus 1 mod q, if this would be the same as sigma to the q plus 2 power, because sigma to the q is the identity. And the reason is, do this twice. If tau sigma tau inverse is sigma to the a, then what about tau squared sigma tau to the minus 2? Well, on the one, that is tau of tau sigma tau inverse. This is supposed to be sigma to the a. So it's tau of sigma to the a tau inverse, which is the same thing as applying, well, it's sigma to the a times sigma to the a times sigma to the a, sigma to the a times, because you break this up as to tau sigma tau inverse times tau sigma tau inverse times tau sigma tau inverse a times, right? That would give you this as you kept canceling out the tau inverses. And then each one of these is sigma to the a, so you get it's a times, so that's sigma to the a squared. When if you take sigma to the a times, that's sigma to the a squared. On the other hand, tau squared is the identity, so this is sigma. Once you square tau, it commutes with sigma. So therefore, sigma to the a squared is equal to sigma, so that implies that a squared is congruent to 1 mod q, and the only elements whose square is 1 mod q are plus or minus 1 mod q. Because if q divides a squared minus 1, this is a minus 1 times a plus 1. And if you have a prime that divides a product of numbers, it has to divide one of them. So either a is 1 mod q or a is minus 1 mod q. So the only possibilities here, this a is not arbitrary. Don't ever think this a is arbitrary. It's related to the order of tau. And in fact, what we proved here, over there, what we proved is that a to the p has to be congruent to 1 mod q. Because you would apply tau, you wouldn't take the square of tau, you'd take the pth power of tau, which you know is the identity. So this a, which is really a number mod q, has to have the property that when you take its pth power, you get to 1 mod q. This is a number mod q, because you just have to know what it is to raise tau to. And it can't be arbitrary mod q, it has to have its pth power being 1. So here, we see that a has to have its square 1. The only two elements mod q whose square is 1 is plus or minus 1. So we have two possibilities. It's sigma or sigma inverse. Just like it was here. If it's sigma, that says tau commutes with sigma. And the group G is isomorphic to the cyclic group of order 2q, generated by tau sigma. And if it's sigma inverse, G is isomorphic to the dihedral group of order 2q, because it has a cyclic subgroup of order q, and it has an element of order 2, and that element conjugates the generator into the inverse. So again, this thing of order 6, it's true for groups of order 2q. It's either cyclic or dihedral. Very simple. Okay, now let's get rid of 2 and try 3. Let's try order 15. Okay, now we're going to do this argument, and I'll kill it for you. First of all, we have this normal subgroup of order 5, generated by sigma. And now we have a subgroup H3, which is 1 tau, tau squared. Now, I'm not going to need this, but I'm also going to show you that this subgroup is normal. I'm not going to need it, but in fact, in this case, H3 is actually a normal subgroup of G2. Both CLOs are normal. That's not necessarily the case here. For example, the elements of order 2 do not form normal subgroups of the symmetric group. We've seen that many times. Okay, why is it normal? Because the number of CLO 3s divides 5, right, and is congruent to 1 mod 3. There are no such numbers except for 1, as number L of CLO 3s divides 5 is congruent to 1 mod 3. Now, it's not the case that this isn't, 3 is smaller than 5, so it's possible that something congruent to 1 mod 3 would divide 5, but nothing does. Right? You get 1, 4, 7. They don't divide 5. So it has to be 1. So L is equal to 1, and it's normal. But we won't need that. Just go over here. We know that tau sigma tau inverse is equal to sigma to the A with A cubed congruent to 1 mod 5. I claim that implies that A is congruent to 1 mod 5. There are no cube roots of 1 mod 5 other than 1. Well, you can just check that. There aren't too many numbers mod 5, so 1 cubed is congruent to 1 mod 5. 2 cubed is congruent to 8, which is congruent to 3 mod 5. 3 cubed is 27, which is congruent to 2 mod 5. And 4 cubed is 64, which is congruent to 4 mod 5. So the only thing mod 5 whose cube is 1, which means that this element has to be equal to sigma, which means that tau commutes with sigma. And in fact, that G is isomorphic to Z mod 15 of Z, generated by sigma tau. So this is a case. It looked like we were getting, both cyclic groups and non-abelian groups and things. But in the case of order 15, there's only one group, and it's cyclic, because you can't solve this equation in a non-trivial way. Okay? Let's go to another group. Order G is equal to 21, which is 3 times 7. Now, in this case, H7 is normal. But H3 may not be normal. We don't know one way or another until we work out the groups. But you see, this argument doesn't work, because the number of CLO there might, we don't know, be 7 CLO 3s. Right? Because the number of CLO 3s divides 7 and is congruent to 1 mod 3. So there could be 1 or there could be 7. 1 CLO 3, or there could be 7. And likewise, in this case, we get a non-trivial solution if we look for A cubed congruent to 1 mod 7. We find that A could be 1. Always 1 works. But also 2 works. And also 4 works. Mod 7. Because if you cube 2, you get 8, which leaves a remainder of 1. And if you cube 4, you get 64, which is 63 plus 1. So it looks like we have 3 possibilities. So we have tau sigma tau inverse equals sigma. That means that tau sigma is equal to sigma tau, commutative group, And it turns out that that's isomorphic to Z mod 21Z, cyclic group of order 21. We could get tau sigma tau inverse equal to sigma squared, or we could get tau sigma tau inverse equal to sigma to the fourth. And it looks like we're getting two other groups of order 21. But we're not. These two give the same group. Give isomorphic non-abelian groups of order 21 with 7 3 silos. Sorry about the movie, people. Isomorphic groups. So you get two groups of order 21, the one where it's equal to 1, and these two give the same group. And why do they give the same group? Well, suppose I made a group where I had this multiplicative relation. Now what's tau? Well, tau is just one of the elements in here. Right? If I chose the other generator for H3, that's tau squared, and tau had the property of conjugating sigma into sigma squared, then tau squared would have the possibility of conjugating sigma into sigma to the fourth. And in this group, there's no preferred tau or tau squared. So if I had a group with a sigma tau that did this, I could make an isomorphism with another group by moving tau to tau squared that did this. And they're isomorphic groups. So it's not that sometimes different values of A give you an isomorphic group. A equal 1 always gives the cyclic group. I should write that down. A equal 1 gives G isomorphic to Z mod PQZ generated by sigma tau. We always know that one. There's always one group of order PQ, the cyclic group. And in some cases, like 15, we only get that. In other cases, like 2Q, we get two groups. Here we get two groups. You can get more. You can get more. Okay, now the book does a great exercise, which I'm going to start for you, where they show you how this quickly becomes more complicated. So we're getting pretty proud of ourselves doing the groups of order PQ. We have a pretty general theory over here. We can work it out in any given case. But suppose we jazz it up just a little bit, and we ask for the groups of order something like P squared times Q. For example, the book does a nice section, which I suggest you go through, and I'll start with you, on the groups of order 12, which is 2 squared times 3. Now here things get much more interesting. It turns out, yeah.
Is it clear that such a group exists?
No. Thank you. Thank you. You actually then, it's not clear. You have to show that this kind of relation doesn't lead you into further contradiction. And there's a method of presenting groups. So this group would be presented, I would say, take the group G generated by sigma and tau, such that sigma to the 7th is the identity, tau cubed is the identity, and tau sigma tau inverse is equal to sigma squared. I'd say, there's your group of order 21. And you'd say, that's very nice. You know, you've now told me how to commute tau and sigma. I know the group is powers of sigma and powers of tau, but am I going to get into trouble with that? Is there some contradiction that's going to come up later where I have some power of some element is equal to the identity but not equal to the identity? And you have to have a way of then proving this group exists. We knew about the dihedral group from geometric construction. So to prove this group exists, this is called, and it's later in the chapter, a Coxeter presentation after a great Canadian mathematician who just died, in fact, at the age of 97, HMS Coxeter. And you have to actually show that you can construct a group with these generators and relations. That's not obvious. But all we can see here is that there's at most one more group beyond the cyclic group. All right, the groups of order 12, turns out that there are 5 distinct groups. Of which 2 are abelian. Two are abelian, so one of them is Z mod 12Z. Another one is Z mod 6Z cross Z mod 2Z, product of two groups. These aren't the same group because this group has only one element of order 2 in it, whereas this group has three elements of order 2 in it. One is the alternating group on 4 letters. One is the dihedral group of order 12. And one is something new that you haven't seen before. And we uncover these groups by going through the same kind of classification, except that it becomes much more complicated. So why does it become more complicated? Well, what we get from the CELO theorem is we have a subgroup H4 in G of order 4, and we have a subgroup H3 in G of order 3. So this group we know is a cyclic group because it has prime order. But this group we just know is an abelian group because it has order p squared. So this can be either isomorphic to Z mod 4Z or to Z mod 2Z squared. So already we have an ambiguity in that we don't know what the structure is of the CELO 2 subgroup. We just know there's something of order 4. And we don't know what the we do know what the structure of the CELO 3 group is. Now in the PQ case, the larger one was always a normal subgroup. Okay? So I claim that in this case neither of them neither of them have to be normal. So let's see what the CELO theorems tell us about the questions of how many CELO 2s we have and how many CELO 3s we have. Well, the number of CELO 2 subgroups has to divide 3, right, and be congruent to 1 mod 2. So what are the possibilities? What are the divisors of 3 which are congruent to 1 mod 2?
1 and 3.
There we go. Okay, otherwise I was going much too fast. So the number L of CELO 2s is equal to 1 or 3. The number L of CELO 3s has to divide 4 and has to be congruent to 1 mod 3. 1 or 4. Good. So in particular, neither of them have to be normal. But I claim one or the other is normal. Namely, you can't have 3 CELO 2s and 4 CELO 3s. You can't have it. It just won't happen. Why? Well, imagine we had 4 CELO 3s. Okay, here's the picture of the group. Here's G. Here's the identity element. And here's a CELO 3. It has 2 non-trivial elements in it, right? Sigma and sigma squared. And we have 4 of those. Now I claim they're all distinct. The only intersection of those groups is the identity. Because they're of order prime. So if you have an intersection of 2 groups of prime order, they have to be the same group. And they're 4 distinct groups. So in each one of these I get 2 elements of order 3. So that gives me 8 elements of order 3. And also I have 1 element of order 1. So there are only 3 elements left in this group that haven't been accounted for, that don't have order 1 or 3. Now, a CELO 4 subgroup contains 3 non-identity elements. So the only possibility is if I had 4 CELO 3 subgroups, the identity plus these 3 elements must be the CELO 4. Because the CELO 4 can't have any intersection with the CELO 3s. For divisibility reasons, again. So then, E union 3 remaining elements have to be a CELO 4, which means there are no other possibilities for CELO 4s. Right? Because they all have to be conjugate. And I've just told you what they are. Which means the CELO 4 is normal. So if we have 4 CELO 3s, we only have 1 CELO 2. So this 4 implies 1. So therefore, at least something is normal. They might both be normal, like in the cyclic group of order 12, or in this group, they're both normal subgroups. But at least one of them is normal. Okay, so the group then proceeds from the fact that at least one is normal, and that we know the structure of these groups to derive the 5 possibilities. I mean, you start off with, okay, let's assume the CeLO 2 is normal. What can we get from that? Okay, let's assume the CeLO 3 is normal. This is a case, by the way, where the CeLO 2 is normal. And this is a case, by the way, where the CeLO 3 is normal, but not the other one. So you can go both ways. So I strongly suggest just to practice working out how the CeLO theorems work, how you put together a group from its inside information. You go through this classification of groups of order 12. It's not the most important thing in the world. It's just a way of testing that you understand the techniques. And as you can imagine, this gets more and more complicated if instead of the group of order 12, I ask for the group of order 24. So the CeLO 2 at order 8, there are already 5 possibilities for that group of order 8. That could be the CeLO 2, let alone how the CeLO 3 is acting on it. So the classification becomes quite a nightmare. Nonetheless, this is the sort of thing finite group theorists love to do. So next time I'm in, I'll bring you in the atlas so you can see all the wonderful things they've done. And Richard will start on Friday with the symmetric group.